Hi, welcome to your Unit 3, Lesson 7B notes. We're going to continue our investigation of real-world applications related to sinusoidal behavior. So let's go ahead and start with example 7. Alternating current is the form in which electric power is delivered to businesses and residences, and it is the form of electrical energy consumers typically use when they plug televisions, lights, and any electric appliance into a wall socket. The current I in amperes following through an alternating current circuit at time t in seconds to model, or it's modeled by the formula I of t is equal to 220 sine of 60 pi t minus pi over 6 for all values of t greater than or equal to 0. So we need to find the amplitude, phase shift, period, all that good stuff. So my A is easy, that's 220. Our period is 2 pi divided by our b, which is 60 over pi, which is going to be, 1 over 30. So really quickly, let's quarter that. So 130 quartered means something's going to be happening every 1/20th. And then my phase shift is my c over b. So pi over 6 divided by 60 pi, which means we're moving to the right 1/360ths. Okay, so graph 2 periods of the function. So since we're assigned, we're going to do an intercept, max, no reflection, intercept, min, and then an intercept. We're shifting to the right 136, which means we're ending, my whole period is 1/30th. So I'm going to be lazy and use my calculator. So 1 over 360 plus 1 over 130. Math fraction gets me 13 3/60ths. All right, so then 1 360 plus my quarter of 1/120. Again, I'm using my calculator to be lazy, is 1/90th. 1/90th, not 190, 1/90th. Adding another 120. Again, I'm using my calculator, so I can be lazy, is 7 3/60ths. Adding another 1/20th. Gets me 1 over 36. And then adding another 1/20th should get me back to that 360. Okay, so now we got to figure out how we're going to label our x-axis. So since I would say we're jumping by 1/20th plus 1/20th, we should probably, I think I'm going to make each of these be a 2 3/60ths. So 2 3/60ths, I know that can be simplified. 4 3/60ths, 6 3/60ths, 8 3/60ths, 10 3/60ths, 12 3/60ths, oops, and then 14 3/60ths. And it's asking for 2 cycles, but that's only going to get us 1 cycle. But at least we'll get a good idea of it. So those reduce to, so 2 3/60ths is what, 1/20th? 1 over 180. And 4 out of 3/60 is going to reduce to 1/90th. 6 out of 3/60 is going to reduce to 1/60th. 8 over 3/60 is going to reduce to 1/45th. 10 out of 3/60 is going to be about 1/36. 12 out of 3/60, little fractions, 1/30th. And 14 out of 3/60 is going to go to 7 over 180. Okay. Anyways, let's actually get the graph in. So my midline is at the x-axis. We are starting at 0 at 1. 3/60th, and then we're going to end at 13 3/60ths, and then my middle is at 7 3/60ths, and then halfway at 190 we're hitting a max of 220. That looks about right. And then at 136 we're doing a minimum of negative 220, like right about there. And then there we have our curve. It's a lot of fraction work right there. Okay, let's go ahead and confirm it with our calculator. Let's go ahead and pull your calculator out. Let's type in our equation, so pause the video as necessary. When you do a zoom trig or a zoom fit, you're going to get something really funky like that, which means we're going to have to manipulate our window. If I do a zoom fit, I might get something a little bit better. I can see it. So here I can see it with 1, 2, 3, 4 periods on the right-hand side. So we can mess around with our window. Like I can make my window be maybe -1 for my x minimum. My x max, since we went out to 13 3/60ths as a decimal, that's just 0.03. So if I double that to get 2 cycles, that's 0.07. So maybe I can go out to 0.08. Y minimum, we need to be lower than 220. So let's do 225. Y max, let's do positive 225. Let's see what that looks like. Oh, that does not look good. We need this window. Our x needs to be smaller. Negative 0.0001. Let's see what that looks like. There we go. That's a little bit better. So then if I trace it, I should be able to see my first, hopefully, x-intercept at 1 3/60th. Yep, there it is. We said our next one was at 7 3/60ths. There it was. And then our last one was at 13 3/60ths. There it is. Okay, and then we could find our maxes and all that good stuff in our mins just to confirm that we were okay. All right, so part C wants to know, where are the x-intercepts for the function? What do they represent in context to the problem? So our x-intercepts are occurring when our argument, right, the stuff inside the parentheses, so that's 60 pi t minus pi over 6 is equal to 0. So if we solve that, 60 pi t is equal to pi over 6, divide by 60 pi, divide by 60 pi, got us t is equal to 136th is our first. And then we can add to it in our general form, so then adding a period each time, either on the right or left. Our period was 1/30th of n, where n is an integer. So what does this mean in context to the current? So this is where the current changes direction from positive to negative or vice versa. From negative to positive. Okay, that concludes example 7. Let's jump to example 8. Cheryl opened up a bakery and found that her monthly profit followed an up and down pattern during the first year. She discovered that her profit could be modeled by P of t is equal to 2t minus 7 sine pi over 3 over t. Again, this is our they're just shifting things around, right? We could put that 2t afterwards. P is measured in hundreds of dollars and T was measured in months after January 1st. Use a graphing utility to find the following. All right, let's go ahead and jump onto our calculator. Okay, I typed in our 2x minus sine of pi x all over 3. If I do a zoom fit, looks like we're not getting anything really nice there. If I do a zoom trig, see if I get something, oh, we got a little bit something better. Okay. So it's saying to use a graphing utility to solve these questions. That means we're probably going to be either doing some tracing, finding x-intercepts, finding max or minimums. Let's go ahead and just make our window a little bit larger. Let's make our y go up higher and our y to go down a little bit lower. Let's do -10 to 10 and see if we can see. Ooh, yeah, look at that craziness that's happening. Looks like it's just going to probably keep moving on with that pattern. Let's try going higher and lower. Let's go -20 to 20. Oh, not 220. Delete 20, and then do my graph. All right, there, that looks a little bit better. Okay, so when did the bakery first begin to make money? So what we need to do, we need to figure out, again, so T represents our time, P represents our profit. So we want our profit to be in the positive, to be making money. So at what point in time in my graph do we start becoming above the y-axis? So clearly you can see at this x-intercept right here. So I can either just trace it over, or I can have my calculator find the 0. Let's make our bound. So I want to find the 0 within which interval. So let's make our left bound our right bound. So it looks like 2.311. So for our first question, it's asking, when did the bakery first start making money? So it was what, about 2.30. So if we're going since January 1st, months after January 1st. So months after, so T of 0 would be January 1st, T of 1 would be February, T2 would be March. So we're gonna be in March. So in March, the function has an x-intercept and it is where P of T starts to become positive. Okay, so in what month did her shop make its greatest profit? In the first year, what was her profit? So now let's go back to our calculator. Bring that back up. Okay, so first month. So that means maybe we got to make our window go out to 12. Maybe let's do 13. Okay, so we want to trace to see our furthest point over, right? So let's trace 12. Oh, can't see it. 24. Make our window maybe higher. And make it up to 30. Okay. So if we said 2 is March, 3 would be April, so really 11 would be December, right? So we want to find our maximum profit in the first year. So let's go and find that max. So second trace, the maximum, get to the left of it, get to the right of it. So it looks like about 10.763. So that would be so 11 would be December 1st. So we're still in November at 10.76 with a profit of 28.26, which I think we're in hundreds of dollars, right? So that'd be what, 2,826. All right, so let's go ahead and write that down. So in November, Cheryl's, I think it's spelled Cheryl, right? Cheryl's Bakery has a profit of about $2,826. Because remember, our point was 10.76, 28.26. All right, let's move on to example 9. Again, keep your calculator handy. Hurricanes are categorized using the Saffir-Simpson hurricane scale. The table below represents the number of major hurricanes in the Atlantic Basin that are rated as major storms of Category 3, 4, or 5 for each decade from 1921 to 2020. So we're going to use a graphing calculator to create a scatter plot for the data for the decades shown below, and then we're going to do a regression on it. So go ahead and get your calculator out. We're going to put our data in L1. So stat, well, first let's clear this out. So we're not graphing that. All right, so stat edit. If you have something in L1, go up to L1, hit clear enter. If you have something in L2, go up, hit clear enter. All right, so what are we doing? We're putting in our 5, 8, 10, 8, 6, and L1. Oh, nope, that's not what we're doing. We're doing our decades over here, that's our X. So 1 to 10. So 1, 2, 3, 4, 5, 6. 3, 4, 5, 6, 7, 8, 9, 10. And then my hurricanes are 5, 8, 10, 8, 6, 4, 5, 5, 11, 9. Okay. So we wanted to see what this looks like as a scatter plot. We can go up to start our stat plot. So second y equals. Enter in plot 1, turn it on. L1. We want to make a scatter plot. There we go. L1 is our X. Let's make L2 be our Y. And then we're going to do a zoom. Stat number 9. And then we can kind of see our regression kind of happening. We got some funkiness happening here. All right, so let's go ahead and do a regression for it. So stat calc. Now remember, this is our world of regressions, the regs. We want to find our trig 1. So we got C, sine reg, enter. When we want our iterations, your calculator will always default to 3 for the iterations. Pretty much what this is it's the maximum number of times our sine reg command will iterate to find the equation. So we can use any number between 1 and 16. 16 generally gives you a more accurate result than smaller integers, but it will take longer for your calculator to do that. So you can just stick to the default of 3. We're not really doing anything that's going to have things being dependent on our calculations. So we'll stick to 3. And then for our period, we don't have to put anything there for the period. So don't worry about that. Let's go ahead and store it though. If we remember, if we hit alpha trace, it's going to give us our options or where we want to store it. Let's store it into Y1 so we have it. And then hit calculate. And then it should come up with our regression for us. Now again, if we were to make our iterations a little bit higher, it's going to change some things. So let me just show you. You don't have to do this. Like if I would have made it 10, let's store this into the second one. And I'll have both of them as options, right? It's gonna change your or not your amplitudes. Do you see how the amplitude changed? So this is a bit more accurate than the one with the 3. So again, it's up to you. If you want to keep it defaulted at 3, that's fine. I would probably tell you on a test what I want your iterations, so it'll make my life a little bit easier on which one I want you guys to do. Okay, so quit out of this. Let's do this again. Stat, edit. I forgot which one number it was. Was it 0? Nope. C. All right, I'm going to do it for 10. Let's do it for 10. I already have that in Y2. Okay, so our function is going to have an amplitude of 3.0627-ish, sine of 0.9778x minus 1.4956 plus, and then there's our midline. So let's go ahead and get that written down. All right, so predicted y, remember we do that for regressions, is equal to 3.0672, nope, too many sevens, 627 sine of 0.9778x minus 1.4956 plus 6.667. Okay, so C wants to know the maximum and minimum number of storms based on our model, so we can get that from the graph. So let's see what it looks like on the graph. Oops, I want to turn out the first one. Get that one out of there. Okay, so second, calculate maximum. Let's get over there to the max. Make my interval that I want to find the max within. So there's our first max. This is at about our max height is 9.7. So about 10 storms. Again, we can round because we're estimating. And then my minimum, 3, again, we're looking for the y value. Enter is about 3.6, so about 4 storms. So for part C, our maximum number of storms, let's say, is about 10, and our minimum number of storms is about 4. Part D, in what decade will the next maximum number of storms occur based on your model? Do you guys need me to write this? So we said our maximum was about 10 storms. Our minimum was about 4 storms. And then we're looking for, will the maximum number of storms occur based on the model? Put it on here. Okay, I got it. So maximum, what decade was that? Well, the next maximum. So our next maximum is going to be over here. So let's calculate our maximum to find our next maximum number of storms. Enter. So about 9.56. Nope, that's still within our period. Okay, so we gotta extend this. Okay, so let's move our max out another 10 decades, so 20. All right, so I think we're looking for this because this was within our data. So my next maximum is going to occur when? So max for, there we go. Here we go. Oh, my goodness, what happened? Come back. Hopefully, there it is. There we go. Okay, so beyond the data that we have plotted, when can we expect the next maximum number of storms to occur, which is about 15.98, so about 16. So what decade would that be? So let's go back to this. So that decade would be, 2071 to 2081? All right, so our next maximum was at 15.98 and some change at 9.7. So this would be, we're doing 2020, which was our last year, plus another 60. So 2071 to 2080 would be our back half of that decade. Okay, let's finish up this little lesson with example 10. The table shows the average temperature per month for Atlanta, Georgia. Information was found from the World Climate website. Plot the data below and notice that they approximate sinusoidal behavior. So January we'll call 1, we're at about 51.6, so maybe right there. February, 55.9. Might be a little bit high, but that's okay. March, 63.7, maybe right there. There. Oh no, I guess that's 65, so sure. April, 72.7, maybe right about there. May, 80.1. June, 86-ish. July, 88. August, 87. September, 82. October, 72.7. Oops, wrong spot. There we go. I'm too zoomed in. November, 62.6. And then December, oops, how did I skip a line? Oops, there's my skipping of a line. Oops. Undo that. This guy needs to go away to there. Okay, needs to go there. Skipped a unit. All right, am I back on track? And then 54. There we go. Okay, so definitely looks like there's a curve to it, right? If we wanted to kind of make a rough plot of it, looks like we're looking something like that. I would imagine that we're going to start coming back up. So I would imagine these would be my low points, and I got about a high point here. So if my high points are about, where are we at for my high points? 88-ish. Let's assume we're at about 88, with my lowest being around 51-ish. So finding that midline from 51 to 88. I got 88 minus 51 gives me a difference of 37. Cut that in half, so about an amplitude of 18.5. Adding that to 51 puts our midline around 70. Well, I guess it's about 69.5. 69.5, right? So these would be your points of reflection happening right around there. All right, so there's our graph. So why does it make sense that the average monthly temperatures can be modeled by a periodic function? I would say something like average monthly temperatures. Average monthly temps will not vary and will not repeat about the same from year to year. Right? It's pretty safe to bet that the temperatures in December are going to be the same as the temperatures as December, right? So temps are cyclical with the seasons. Temps are cyclical with the seasons. Okay, so moving on to the next page, we're going to focus on part C. So part C says, let's model this graph with a sine function in the form of y equals a sine b of x plus d. All right, so we kind of went through, so amplitude, let's actually use the highest point. So 88.5 or 3 minus 51.6, cut that in half, it's going to get us our amplitude of 18.35. Our D, or our midline, is going to be 88.3 plus that 51.6, cut in half, which is about 69.95. Our period, so 2 pi over b, looks like a full period is 12 months, right? So that means b is going to be equal to pi over 6. So the model that we're getting, just pulling from the values that were given to us, is about 18.35 sine of pi over 6 x or t, whatever you want to use, plus 69.95. So let's see how good that model is compared to what the calculator gives us. So type in your results, that data in the table. L1 is going to be 1 through 12. L2 is going to be all of the actual values. Let's go over to style calculate, down to C. Sine reg. Yeah, let's go to 10 iterations, why not? And then let's store it just so we have it. Calculate. All right, how do we do? 19.3697 sine 0.47. What is pi divided by 6 as a decimal? So 3.14 divided by 6 is about 0.5233, so pretty close, 0.477. There's our phase shift, and then there is our D. So let's go ahead and write this down. All right, so we modeled it. Here we have y is equal, predicted y is equal to 19.37 sine of 0.477 x minus 1.764-ish plus 69.6. All right, so part E, explain the meaning of the points of inflection in context to the data. So our first point of inflection, we can go back to our graphing calculator. Where are we here? Okay, so if we graph it, oops, let's do a zoom 9 so I can see the scatter plot. There we go. I'm going to put in that midline, let's clear that out, at 69.6. So when I graph it, now I can see where those point of inflections are, so I can have the calculator find them for me. So I want to find the intersection of that graph, that graph. There's our first point of inflection. So 3.69, that puts us in, what, the month of, one is January, February, March, so kind of close to the middle of March, right? That's when our weather starts warming up. So we're going from spring to summer, I guess, right? And then our second one's going to be over here. So let's do a second calculate trace. Let's see if we can find the other one. Intersect. If I move over this way, will it give me that intersection? Let's see. Enter, enter, enter. There it is. So 10.28. So that puts us in, what, October? So October to November is where our temperatures start decreasing, right? Because we're getting smaller here. Okay, so let's write this out. So explain the meaning of the points of inflection. So our first point of inflection was at 3.7-ish, if we round it. It was about 69.6 at our midline. So that means in the end, or at the end of March, getting close to April, our weather warms up. And then our second one was 10.28, 69.6, which means in October, the temps are decreasing. All right, for F, explain the meaning of the maximum and minimum values in the regression model. Okay, so let's use our calculator to come up with our max. So second trace maximum. Let's get the interval that I want the calculator to find the maximum between. So maybe as such. So we have a maximum of about 7 at 88. So month of 7 is what, July? We're going to get a maximum temperature of about 88.97. And then my minimum, I'm going to move my window so I can see X-min. Let's go out to the right maybe. Let's make my X-max 20. And then we can be in, there we go. So second, calculate minimum. Let's go find the minimum over here. Oops. All right, so 13. So going a loop around 12, that would be 1. So January. So January, we have a minimum temperature of about 50.23. All right, so let's write this out. So we have a max temp of 88.97 degrees Fahrenheit in July. And then we have a min temp, sorry for my really bad handwriting, of 50.23 degrees Fahrenheit in January, which seems interesting. I feel like it would be a lot hotter in Georgia than 88.97 degrees, but who knows? All right, there ends your notes.